Hello everyone. Today in this lecture I am going to discuss the concept of diagrams in the unified modeling language. So first of all, a diagram is the graphical representation of a set of elements and most often rendered as a connected graph of vertices and paths. Here the graph of vertices means things and the paths is also known as the relationships. You draw diagrams to visualize a system from different perspectives. So a diagram is a projection into a system. For all but the most trivial system, a diagram represents an elided view of the elements that make up a system. The same element may appear in all diagrams, only a few diagrams, or in no diagrams at all, the same element may appear. In theory, a diagram may contain any combination of things and relationships. In particular, however, a small number of common combinations arise which are consistent with the 5 most useful views that comprise the architecture of a software-intensive system. For this reason, the UML includes 13 kind of diagrams. So we will see these diagrams one by one and how these diagrams are used, what is the purpose of the diagrams. So first diagram is class diagram. The second is object diagram, and then use case diagrams, sequence diagram, collaboration diagram, state diagram, activity diagram, component diagram, and then deployment diagram. So the first diagram is class diagram. So class diagram shows a set of classes, interfaces and collaborations and their relationships. These diagrams are the most common diagrams found in modeling object-oriented systems. So class diagrams address the static design view of a system. Class diagrams that include active classes address the static process view of a system. And the component diagrams are variants of class diagrams. So we can say that class diagram is a static diagram. It represents the static view of an application. And class diagram is not only used for visualizing, describing and documenting different aspects of a system, but also for constructing executable code of the software application. So class diagram describes the attributes and the operations of a class and also the constraints imposed on the system. The class diagrams are widely used in the modeling of object-oriented systems because they are the only UML diagrams which can be mapped directly with object-oriented languages. So class diagram shows a collection of classes, interfaces, associations, collaborations and the constraints. It is also known as a structural diagram. So if someone asks what is the purpose of class diagrams, then the purpose of class diagram is to model the static view of an application. Class diagrams are the only diagrams which can be directly mapped with object-oriented languages and thus widely used at the time of construction. UML diagrams like activity diagrams, sequence diagrams can only give the sequence flow of the application. However, class diagram is a bit different. It is the most popular unified modeling language diagram in the coder community. The purpose of the class diagram can be summarized as analysis and design of the static view of an application, describe responsibilities of a system, base for component and deployment diagrams, and forwarding and reverse engineering. Okay. Class diagrams is also considered as the foundation for the component and deployment diagrams. Now the next is an object diagram. An object diagram. What is object diagram? It shows a set of objects, their relationships. Object diagrams represent static snapshots of instances of the things found in the class diagrams, and these diagrams address the static design view or static process view of a system, as do class diagrams, but from the perspective of real or prototypical cases. So an object diagram is the diagram that shows a complete or partial view of the structure of a modeled system at a specific time. Likewise, a static. So, object is an instance of a class in a particular moment in runtime that can have its own state and data values. Likewise, a static UML object diagram is an instance of class diagram. It shows a snapshot of the detailed state of the system at a point in time. Okay, now the next one is use case diagram. A use case diagram shows a set of use cases and actors, means a special kind of class and their relationships. Use case diagrams address the static use case view of a system. So these diagrams are especially important in organizing and modeling the behaviors of a system. To model a system, the most important aspect is to capture the dynamic behavior. So there are internal and external agents are known as actors. Use case diagrams consist of actors, use cases and their relationships. The diagram is used to model the system, subsystem of an application. A single use case diagram captures a particular functionality of a system. Hence, to model the entire system, a number of use case diagrams are used. Now, what is the purpose of use case diagrams? The purpose of use case diagram is to capture the dynamic aspect of a system. However, this definition is too generic to describe the purpose, as other four diagrams, activity, sequence and collaboration, and state chart diagrams, also have the same purpose. So we will look into some specific purpose which will distinguish it from other four diagrams. Use case diagrams are used to gather the requirements of a system, including internal and external influences. These requirements are mostly design requirements. The purpose of use case diagrams can be said to be used to gather the requirements of a system first, and the second is used to get an outside view of a system. Outside view of a system. And it is used to identify the external and internal factors influencing the system. It shows the interaction among the requirements are actors. So after this use case diagram, sequence diagrams. Sequence diagrams and communication diagrams are kind of interaction diagrams. So what is interaction diagrams? Interaction diagram shows an interaction consisting of a set of objects or roles, including the messages that may be dispatched among them. Interaction diagrams address the dynamic view of a system, and a sequence diagram is an interaction diagram shows an interaction consisting of a set of objects or roles, including the messages that may be dispatched among them. So interaction diagrams address the dynamic view of a system. A sequence diagram is an interaction diagram that emphasizes the time ordering of messages. A communication diagram is an interaction diagram that emphasizes the structural organization of the objects or roles that send and receive messages. Sequence diagrams and the communication diagrams represent similar basic concepts, but each diagram emphasizes a different view of the concept. Sequence diagrams emphasize temporal ordering, and the communication diagrams emphasize the data structure through which messages flow. So timing diagram shows the actual times at which messages are exchanged. So these are the diagrams. Now the next is state diagram. A state diagram shows a state machine consisting of states, transitions, events, and activities. A state diagram shows the dynamic view of an object. They are especially important in modeling the behavior of an interface, class, or collaboration, and emphasize the event ordered behavior of an object, which is especially useful in modeling reactive systems. So this is the state diagram. Now an activity diagram. An activity diagram shows the structure of a process or other computation as the flow of control and data from step to step within the computation. Activity diagrams address the dynamic view of a system. They are especially important in modeling the function of a system and emphasize the flow of control among objects. Okay. So activity diagrams are graphical representations of workflows of stepwise activities and actions with support for choice, iteration, and concurrency. Okay. In the unified modeling language, activity diagrams are intended to model both computational and organizational processes. Organizational processes, that is, workflows, as well as the data flows intersecting with the related activities. Although activity diagrams primarily shows the overall flow of control, they can also include elements showing the flow of data between activities through one or more data stores. So this is the concept of activity diagram. Now the component diagram. Component diagram shows an encapsulated class and its interfaces, codes and internal structure, and consisting of nested components and the connectors. Component diagrams address the static design implementation view of a system. They are important for building large systems from smaller parts. UML distinguishes a composite structure diagram, and that is applicable to any class from a component diagram. But we combine the discussion because the distinction between a component and a structured class is unnecessarily subtle. Now we can summarize it in unified modeling language. A component diagram shows how components are wired together to form larger components or software systems. They are used to illustrate the structure of arbitrarily complex systems. Okay. What is the purpose of component diagrams? Component diagrams is a special kind of diagram in UML. The purpose is also different from all other diagrams discussed so far. It does not describe the functionality of the system, but it describes the components used to make those functionalities. Okay. The purpose of component diagrams can be to visualize the components of a system, to construct executables by using forward and reverse engineering, to describe the organization and relationships of the components. So this is the component diagram. Now the deployment diagram. A deployment diagram shows the configuration of runtime processing nodes and the components that live on them. Deployment diagrams address the static deployment view of an architecture. A node typically hosts one or more artifacts. So a deployment diagram in the unified modeling language, the physical deployment of artifacts on nodes. To describe a website, for example, a deployment diagram would show that what hardware components exist, what software components run on each node, and how the different pieces are connected. For example, using JDBC, REST, RMI. So the nodes appear as boxes and the artifacts allocated to each node appear as rectangles within the boxes. Nodes may have subnodes which appear as nested boxes. A single node in a deployment diagram may conceptually represent multiple physical nodes, such as a cluster of database servers. So there are two types of nodes in the deployment diagrams: device node and the execution environment node. So device nodes are physical computing resources with processing memory and services to execute software, such as typical computers or mobile phones. An execution environment node, that is EEN, is a software computing resource that runs within an outer node and which itself provides a service to host and execute other executable software elements. Now, the rules of the UML. What are the rules of the Unified Modeling Language? The Unified Modeling language building blocks cannot simply be thrown together in a random fashion. Like any language, the UML has a number of rules that specify what a well-formed model should look like. A well-formed model is one that is semantically self-consistent and in harmony with all its related models. The UML has syntactic and semantic rules for names. Names means what you can call things, relationships, and the diagrams. The UML has syntactic and semantic rules for scope. Scope meaning the context that gives a specific meaning to a name. Visibility, how those names can be seen and used by others. This is the concept of visibility. Now next is integrity, how things properly and consistently relate to one another. Next is execution, what it means to run or simulate a dynamic model. The rules of the UML encourage you but do not force you to address the most important analysis, to address the most important design, implementation questions that push such models to become well formed over time. So these are the rules of UML. So 5 rules for better UML diagrams. One is to avoid large diagrams with too many items. First one is this. The second one is avoid any two lines in your diagram crossing each other. We should avoid such type of situation. Third is lines in a diagram should go only horizontal or vertical with only right angles. Fourth is parent elements are higher than the child elements in the generalization or realization hierarchies. And last one is diagrams should be nice and clean. Diagrams should be nice and clean. So these are the rules of the UML. Okay, now common mechanisms in the UML. A building is made simpler and more harmonious by the conformance to a pattern of common features. A house may be built in the Victorian or French country style largely by using certain architectural patterns. So that define those styles. The same is true for the UML also. It is made simpler by the presence of four common mechanisms that apply consistently throughout the language. So these are the common mechanisms in the UML. First one is specification, second one is adornments, third is common divisions, and fourth is extensibility mechanism. So what is specification? The UML is more than just a graphical language. Rather, behind every part of its graphical notation, there is a specification that provides a textual statement of the syntax and semantics of the building block. For example, behind a class icon is a specification that provides the full set of attributes, operations including their full signatures, and the behaviors that the class embodies. Visually, that class icon might only show a small part of this specification. Okay. Now the UML's specifications provide a semantic backplane that contains all the parts of all the models of a system. Each part related to one another in a consistent fashion. The UML's diagram are thus simply visual projections into the backplane. Each diagram revealing a specific interesting aspects of the system. The second one is in adornments. Most elements in the UML have a unique and direct graphical notation that provides a visual representation of the most important aspects of the element. For example, the notation for a class is intentionally designed to be easy to draw because classes are the most important element found in modeling object-oriented systems. The class notation also exposes the most important aspects of a class, namely its name, its attributes, and the operations. Okay, so this is the adornments. Third one is common divisions. And in modeling object-oriented systems, the world often gets divided into several ways. There is the division of class and object. A class is an abstraction. An object is one concrete manifestation of that abstraction. In the UML, you can model classes as well as objects, as shown in the diagram, shown in the figure. Graphically, the UML distinguishes an object by using the same symbol as its class and then simply underline the object's name. So this here it is written customer and its name, address, phone. Okay. So in this figure, there is one class named customer together with three objects. Customer is a class and there are three objects. Jan, which is marked explicitly as being a customer object. Customer, an anonymous customer object, and else, which in its specification is marked as being a kind of customer object, although it is not shown explicitly here. Almost every building block in the UML has this same kind of class object dichotomy. For example, you can have use cases and use case executions, components and component instances, nodes and the nodes instances, and so on. Second, there is the separation of interface and implementation. An interface declares a contract, and an implementation represents one concrete realization of that contract, responsible for faithfully carrying out the interface's complete semantics. So in the UML, you can model both interfaces and their implementations as shown in figure. So in this figure, there is one component named spelling wizard.dll that provides two interfaces, I unknown and I spelling. So it requires an interface I dictionary that must be provided by another component. So this is shown in this diagram. Almost every building block in the UML has this same kind of interface implementation. The third is there is the separation of type and role. Okay, this is the part with role and type, ticket order, and there is customer with person. Extensively mechanism. So this topic I will discuss in the next lecture. Thank you.